Hi, this is my video tutorial of the Test 1 wrapper. I will be solving problem 4, and this was the problem that gave me the most trouble during the exam. So this problem started off with a rock climber with a mass of 60 kilograms and who's ascending a vertical wall and stops for rest by leaning on her rope as seen in the diagram. So we'll draw a quick free body diagram here. So the rock climber is this point here. Then you have the force of gravity, Fg here. Then you have the force of the wall, which she's leaning up against. And then you have the force of tension, F of t here. And so she's 15 meters away here. And this degree here is 31 degrees. And this here is 15 degrees. So in part A of the question, it asks, determine the magnitude of the tension in the rope required for the mountain climber to remain stationary. So it says, please start from the fundamental principle and show your work. So the fundamental principle that we're starting from is the momentum principle. So in this, we know that the rock climber is not moving. So we know that dp dt is equal to 0. And since dp dt is equal to 0, we also know that Fnet is equal to 0. So Fnet and dp dt are equal to each other. So you essentially next want to find both the x and y components of your forces. So for your x components, which would be here and here, your x components will be the force of the wall times the cosine of 15 degrees minus tension force times the sine of 31 degrees. And that is equal to 0 since we're going back to our original principle of dp dt is equal to Fnet, which is equal to 0. So our y component of our force here is the tension force times the cosine of 31 degrees from our diagram here, minus the force of gravity, which is mg, mass times gravitational force, plus the force of the wall acting on the climber, times sine of 15 degrees. So next what we do is we can take either of these equations and solve for either f of w or f of t in terms of the other variables. So what I'm going to do is solve for f of w in terms of f of t. So I'll take this equation here and solve for f of w. So then you get f of w is equal to f of t, little brackets here, is equal to f of t times the sine of 31 degrees divided by cosine of 15 degrees. So we've solved for f of w in terms of f of t, which is here. So next what you'll do is you'll take this equation here and plug it into the y component equation that we've gotten here, and plug this f of w here into f of w here. So we'll do that real quickly. So you have f of t times sine of 31 degrees divided by cosine of 15 degrees times the sine of 15 degrees plus f of t cosine 31 degrees, I'll have to go to the next line here, minus force of gravity, that is all equal to 0. So you can see here, this is where we're at now. So from there, we're going to solve for f of t since we are solving for the magnitude of the tension of the rope required for the mountain climber to remain stationary. So then as we solve for f of t, you get, I'll just go to the next line here. F of t is equal to mg divided by sine of 31 degrees times the tangent of 15 degrees plus the cosine of 31 degrees. And the way I got that was since sine over cosine is equal to tangent, these two multiply and equal tangent of 15 degrees. And then these two components here go together, and then you can pull out the f of t here, and that's what you're solving for. And then you can move the mg here over to where 0 was before, and then so you're essentially just solving for f of t. So then after you have your equation here, f of t is equal to mg sine of 31 times tangent of 15 degrees plus cosine of 31 degrees. You can plug in your mass and universal gravitational force. So f of t becomes 60 kilograms times 9.81 meters per second, all over sine of 31 degrees times tangent of 15 degrees plus the cosine of 31 degrees. So after plugging all that into a calculator, which is straightforward obviously, you get the ultimate answer of 591 newtons. So that is your answer for part A. So for part B here, part B says, determine the magnitude of the wall force F required for the mountain climber to remain stationary. So again, we have to start from a fundamental principle and show our work. So if we go back to our fundamental principle here, we know that dp dt is equal to F net, which is also equal to 0 because the rock climber is not moving. So then we can also go back to one of our original equations here that we got from our free body diagram. And so we also know the force of the wall times cosine 15 degrees minus force of tension times sine of 31 degrees is equal to 0. And we got this equation from our x component from our free body diagram here. So that's where this is coming from. So then we're going to simply solve for the force of the wall, which is what we're solving for ultimately in this problem. So we solve for f of w here is equal to f of t, so the tension force, times sine of 31 degrees divided by cosine of 15 degrees. So all I did here was move the tension force over to the other side of the equation and then divide by cosine of 15 degrees. So then here we already know what the tension force is because we've already solved for that in part A of the problem. So we know that that value is 591 newtons. So we can plug that in for f of t, and then the rest of this is plug and chug using the calculator. So then we know that the force of the wall is equal to the 591 newtons that we got before times sine of 31 degrees divided by the cosine of 15 degrees. And using the calculator again, we get the result of 315 newtons once plugging that into the calculator. So that is your answer for part B. So our final problem here, last part, is part C. And part C asks, calculate the minimum static coefficient of friction between the climber's shoes and the cliff required to remain motionless in the position shown. So to start off here, we're going to draw another free body diagram. And so the rock climber's shoes are here, leaning up against a perpendicular wall here. And so the rock climber's shoes experience force of friction here. So the rock climber's shoes are pressing up against the wall. Then you also have the force of the wall, which is pushing up, which has its horizontal and vertical components, and that was f of w. Then you've also just got a little line drawn here, so you've got your triangle here, and a 15-degree value of the angle between the shoes and the climber and the wall. So then we know that the force of friction is equal to mu, which is the coefficient of friction, times the force of friction acted on by the wall here. So then we can also assume, since the shoes of the climber are pushing up against the wall, we know that this is the point at which the shoes will almost just before the shoes will slip, so that's at a maximum. So originally this was less than or equal to mu times force of friction, but we know that since it's at a maximum, it's no longer less than, it's equal to. So we know that the force of friction is equal to mu times f of n. So after that, so essentially we're assuming that the force of friction on the shoes is maximum because they're about to slip. So then we know that f of n is equal to f of w, coming from right here, times cosine of 15 degrees, which you're essentially doing a little SOHCAHTOA. So you know that cosine is opposite over hypotenuse, so you have f of w times cosine of 15 degrees. And then you know that the force of friction here is equal to, so you have your f of friction is equal to force of the wall again, times the sine of 15 degrees. So these are your two components of f of n here. So then you have to bring your mu, the static coefficient of friction, in again. So you bring that into the equation. So you have mu times f of w times the cosine of 15 degrees from our first equation here is equal to f of w times the sine of 15 degrees is equal to the sine of 15 degrees. So finally, you're going to solve for mu here and bring this over to the other side. So you know that mu s, or the static coefficient of friction, is equal to the sine of 15 degrees divided by the cosine of 15 degrees. So that's essentially the tangent of 15 degrees. And after plugging that into the calculator, you get that the final value of that is 0.268, which does not have a value. And so you get the last three answers, you get all three answers here of problem 4, and this concludes the test 1 record for midterm 1.